Here we are in Calc 1, Chapter 3, Section 8. Chapter 3 is about differentiation rules, and in this section, we're going to talk about exponential growth and decay. And we're going to talk about them in a way that's definitely next level from what you might remember from a college algebra class. Let's see what we've got. Now, there's only 40 slides that we're going to look at, so this shouldn't take very long. I'm going to go through these slides. I want to talk a little bit about concept. I'm going to give a little bit of the backstory behind some of these formulas and functions. I'm going to try to not go totally insanely deep on these, but I want you to have at least seen where some of these things come from and how they relate to the more elevated level of sort of mathematical inspection that we take in a calculus class versus what you see in an algebra class. So let's talk through a couple of things. We'll see some example problems printed up for us in these notes provided for Stewart's 8th edition calculus book, and then I'll toggle over and look at a couple of homework problems in WebAssign. So what we're seeing and what you're seeing on this slide is that there are, you should read this, honestly, but what we're talking about is the description of the rate of change of a population of something, whether it's something living, or if we're talking about carbon dating something, in which case we're talking about something that's non-living and it's decaying versus a population that's maybe growing. And at the core of this mathematically is this. It's this relationship right here. And what it says is, and what we're going to see a little bit more clearly on the next slide, I believe it is, this is talking about how this particular concept applies in nuclear physics and in chemistry and in finance. We're going to see some examples of those. And here's that same relationship that I circled just using different notation. We've got the rate of change of y, so dy, with respect to time, dt, is equal to k times y. Now k is a constant, as you're seeing here, and the y value that you're seeing, well, you're seeing two of them, and it's interesting they're the same. So this equation involves the derivative of a function, y, and the original function, all in the same equation. And what it says is that the rate of change of y with respect to t, so that's dy dt, is proportional to, that's the k value, its size, y of t at some particular point in time. So there's this relationship, this proportional relationship between the rate of change of a thing and the thing itself. When we're talking about populations, often we're talking about growth. When we're talking about carbon dating something, for example, we're talking about decay. In the case of growth, our k value, our constant, is going to be positive or larger than 0. With decay, our k value will be less than 0. So again, what we have here is a function, y, whose derivative is proportional to the function itself. It's a constant multiple of itself. And what we discover is, and this is where we're not going to go all the way down the rabbit hole, is what we discover is that the exponential function that takes on this form, where c is a constant, satisfies this relationship where the derivative of an exponential function does end up equaling a constant multiple of the original function. And you know this now from having taken the derivative of e to the power of some function. Except this function is more simple than that. It's the derivative of a constant value times e to the kt. What is the derivative of, let's say we just had maybe m equals e to the kt. What's the derivative of that? dm over dt would equal e to the kt times the derivative of the exponent, which in this case is k. You take that k value, you swing it and put it in front of this e to the kt. K is a, oh, look, there they are. Right, there's the coefficient of k, and your function, y of t, is your exponential function. So I actually like the way that this is printed out, because the derivative of y is equal to, there's the constant value, here's the k that multiplies out front because of the chain rule when it comes out of the exponent, and you take the c and the k and you have them switch places. Now the k is out front, but of course c times e to the kt is the original function y of t. So we replace c times e to the kt with y of t, and we have dy dt equals k times y of t. So that's about as far into the backstory as I'm going to go. The c value is something that has to be calculated, so I want to talk about that for a moment. We see later that any function that satisfies this relationship must be of the form, and then I went in here very small. I had to zoom way in to write this. I much prefer that this is, instead of just saying y equals, I like this to say y of t equals c times e to the kt. And I like that because the very next thing that we see is y of 0. So I want you to know that that 0 that I'm pointing at there is a time value. It's the t value, which is why this t is now appearing here as a 0, because these zeros are the same 0. They're time values. Now when t is equal to 0, that's usually the beginning of a process. Right when you hit the button on the stopwatch, t is equal to 0. So we call, well, first the arithmetic of it. When you take e and you raise it to the power of 0 times k, you end up with c times e to the power of 0. And anything to the power of 0 is equal to 1, so now you have c times 1, which of course is equal to c. So our initial value, y of 0, is equal to c. So that idea of a t value being 0 when time is first starting, that's when the process is being initiated, so we'll call that the initial value. Which takes us into theorem number 2. They're calling it here. The only solutions of the differential equation, dy dt equals ky, are this sort of family of exponential functions, where the coefficient y of 0 has to be calculated using some given functions. So let's talk about growth first. So this is where our k value is going to be positive. And I've written a couple of additional sort of initial notes into these notes. So what's the significance of the proportionality constant k? In the context of population growth, where p of t is the size of a population at time t, we can write, and so the notation has changed a little bit here, but I want you to remember it's the same as this notation, so make sure that those are equivalent in your mind. The derivative of p with respect to time is equal to some constant times p, where p is a function of time. See how it's just being called p here, but really p is population as a function of time. It can be a little bit confusing, so that's why I keep trying to point that out. If we take this equation and we solve it for k, I don't know what that was, then we get this equation. So 1 over p times dp dt is your k value. It's your growth rate divided by the size of the population. And what we do is we call that the relative growth rate. So that can go into your notes for a bit of a definition. we're taking the rate of growth of the population and dividing it by the population. Interesting. And that's our k value, the relative growth rate. It's almost like the growth rate per person, right? We're dividing by the total population. So according to number 3, instead of saying growth rate is proportional to the population size, we could say that the relative growth rate is constant. Why would we say that? Well, because at some particular point in time, these numbers are going to be fixed and the k value is going to get locked into place. It's this relationship that's going to persist through time. And so that relative growth rate is going to end up being constant, which is really fascinating that that actually happens. And we're talking about, in the case of radioactive decay, we can be talking about millions of years, and that k value is going to remain the same as the relative growth rate. So we take these things and we sort of stir them together, and number 2 ends up saying that the population with a constant relative growth rate must grow exponentially. And exponential growth you might remember from an algebra class, where capital A equals capital P times e to the RT. Take that C value right there, replace it with a capital P, and it looks like PERT. Except instead of R, there's a K value. But the R is a growth rate, and K here is also a growth rate. Unless it's negative, then it's a decay rate. So these things are very related. We're just getting a little bit more of the backstory here. For instance, so we've got P prime equals KP. That's just another way to write it. The rate of change of population with respect to time is equal to, and we're seeing that our K value is 0.02. So that is our relative growth rate. That's our K value, is 0.02. T is measured in years. We know that our C value is the initial value. Here it's being expressed as P sub 0. You could also think of it as P of 0. And if we had a population equation, we could take 0, plug it in, and get the initial population. So there's too many variables and too many subscripts and so on. Let's look at a real example. So we're going to use the fact that the world population was 2,560 million. So it's a weird scale, but we're measuring things in millions here. In 1950 and 3,040 million in 1960. And we're going to use that information to model the population of the world in the second half of the 20th century. So that'll take us all the way through the end of 1999. And we're going to assume, because of the section of the chapter that we're in, that the growth rate is proportional to the population size. In other words, that P prime is equal to K times P. And we're being asked, what is the relative growth rate? And we know now that relative growth rate is our K value, and that is equal to 1 over P times, in this case, dP dt. Use the model to estimate the world population in 1993. And predict it, extrapolating it all the way out to 2020. So here's our solution process. We're going to measure the time t in years, and we're going to pretend that t equaling 0 is sort of the start or the beginning of our inspection of what's going on with the world population, and that examination is starting in the year 1950. So a t value of 0 corresponds to the year 1950. And we're going to measure the population. We're going to call it P of t. It's going to be measured in millions of people. And that starting value when t equals 0 is the population of the world in 1950, which was 2,560 million people. And we were told that 10 years later, in the year 1960, the population of the world was 3,040 million. And since we're assuming that this relationship holds true, Theorem 2 tells us that our population function can be described as our initial population times e to the kt. And we know because we were told that in the year 1950, our initial population was 2,560. That's being measured in millions. We were also told that 10 years later in the year 1960, that our population in 1960, so P sub 10 was equal to 3040. And we should be able to arrive at that by taking our initial population and multiplying it by E to the, now this, I don't really like that it was typed up this way. If you're writing these notes down by hand, I would recommend that you switch these two things, because I think it's beneficial to write them in the same order. Up here it says KT, here it says TK. I don't like that. I want to be able to visually see the things changing, have them line up, okay? So it's the T value that's changed to a 10 because we are 10 years after the beginning of our inspection in the year 1960 now. We can use this equation now to find our K value. So we have to solve that equation for K. That process, let's work that process out. You should see that. Take this, I'm not really prepared with a calculator for this. So I'm gonna do it all and make it calculator ready, and then you'll type it into the calculator. But, well, and we're given an approximate value here anyway. But I'm gonna take this equation, I'm gonna divide both sides by 2,560. So I now have e to the 10k, or k10, equals 3040 over 2560. And then I'm going to take the natural log of both sides. Natural log of e to the, I'll write k10 this time, is equal to the natural log of this terrible fraction, 3040 over 2560. Now, by properties of logarithms, I can take this exponent and bring it out in front of the natural log like it's a coefficient. Or, if I know my properties of natural logs, I know that natural log and e to the power are inverse functions. Those two are going to cancel each other out, leaving me just with k times 10 on the left-hand side equals the natural log of our fraction. And then we divide both sides by 10 or multiply both sides by 1 over 10. And we get this. Type that into a calculator and you'll get approximately 0.017185. So that's our K value. Now, if you're using a graphing calculator, actually, I'm going to go grab my calculator, BRB. Okay, so I have a TI-84 here, and on my screen, which I don't think you're able to see, I'm not using a webcam, so it doesn't like automatically adjust focus and contrast and brightness and that stuff. But I typed in this expression that you're seeing on the screen, this 1 over 10 times the natural log, and I got a number, and it's on my screen. And what I wanted to remind you that you can do is that here in the bottom left, or almost just above the on button, if you have this calculator, there's a button that says STO with an arrow on it. And if you hit that button, now on my screen up here, it says answer with a little arrow next to it. And you can take this exact value, not just approximately 0.017185, but the infinitely long decimal. You can take that and store it in any variable that you want. Not just the x variable, which would be accessed by hitting this button here, your normal variable button, but if you hit, let's see, which color do I need? The letters, the entire alphabet worth of letters that are above my keys here are written in green. So if I hit my alpha button near the top left, I can then select any letter I want to, and I might find the letter P, which on my keyboard is above the number 8. So I hit alpha and then 8, and it puts a P next to it. Now it says answer with an arrow and the letter P, and if I hit enter, I see that same decimal appear. It just types out the same decimal again, but I know that that exact value is stored in my p variable. So just in case I need to use it in the exponent position again for a future calculation, I don't have to type it all in again. I don't have to type in all this natural log stuff. I don't even have to type in the approximate decimal value. I can use the exact value by just typing in that p again. All right, so there's a little bit of some calculator assistance for you. So we have our k value, and I don't even remember what we're doing anymore. Let's find out. The relative growth rate is about 1.7%. That's this number as a percentage, so just slide the decimal over 2 places. And here we're seeing our p of t function with our new k value in place and our starting value, our starting population in the year 1950. If you're writing all this down, you want to be labeling components and the numbers in the correct places of these equations. Not a bad idea. Now we're being asked to estimate the world population in 1993. And the year 1993 is 43 years after the year 1950, which is why we're seeing the number 43 right here and right here. And that's just pure calculator work. Type that in. It gives us a population of approximately 5,360 million. And in the year 2020, which is 70 years after 1950, we've typed in the 70 here. The 70 is appearing as our time value. Calculator work gives us this approximate population. What you're seeing here is a graph of the equation that we just created from 0, a t value, right? These are t values, from a t value of 0 through a t value of 50. And the points that are plotted here are the populations in 1950, 1960, and then our approximations are there also. And in the year 2000, we've got this value here. So you can see that some of these points, they go a little bit more astray. So these are the blue dots are the actual world populations, and this magenta curve is the function that we designed. And you can see that it's not that far off. It's a pretty good approximation. The farther you take the curve into the future, the greater the chance is that it's going to deviate from what the actual numbers end up being. So I don't know what the actual population is today of the world, or even the approximation of the population today, but you should jump on the internet and see what the current population is and compare it to the population that was predicted here for the year 2020. So there we were talking about population growth. Now we're going to talk about radioactive decay. So we're going to be using a k value that's negative, and we're going to not get buried in the details of this process, but we're seeing that same kind of a relationship. We're seeing that k value. There's change going on with respect to time. M here is referring to mass. And when we're looking at radioactive decay, radioactive substances, it says, decay at a rate proportional to the remaining mass, as opposed to the current population, which is on its way up. And here we're seeing m sub 0, which is the same thing as m of 0. So it's this initial amount or initial mass of a radioactive substance. There's your e to the kt. And you've heard this expression before, half-life. So physicists express the rate of decay in terms of half-life, the amount of time required for half of any given substance to decay. And in example 2, we're told that the half-life of radium-226 is 1,590 years. There's a sample of radium-226 that has a mass of 100 milligrams. We want to try to find a formula for the mass of the sample that remains after T years. And then we want to find the mass that we think is going to remain after 1,000 years, specifically. Correct to the nearest milligram. It's pretty demanding. And we want to know when will the mass be reduced to 30 milligrams. So our function m of t is going to represent mass remaining after T years. And because it abides by this format, we know that we're going to need an initial mass. And thankfully, this problem gave us an initial mass of 100 milligrams. So m sub 0 has all of a sudden been replaced by m of 0. And we know, because the problem gave it to us, that that value is going to be 100. So now we've got the beginnings of a function. M of t no longer just equals m sub 0 times e to the kt. Now it equals 100 times e to the kt. Problem is, we don't have a k value yet. In order to determine the k value, we're going to use the fact that this substance has a half-life of 1,590 years. So if we plug in the 1590 as our t value, we know that we're going to end up with half of what we started with. In other words, half of 100. So our t value of 1,590 years goes in here. Our initial starting amount of 100 milligrams goes in here. We know that after 1,590 years, we're going to have half of it left. So there's the remaining 50 milligrams. And the only unknown in this equation is our k value. Divide both sides by 100, and you've got e to the 1590k equals 1/2. Take the natural log of both sides and divide by 1590, and you'll have a k value that is, oh right, here's the, sorry. When we take the natural log of both sides, the e disappears, leaving us with the 1590k. And on the right-hand side, we're going to have the natural log of 1/2. The author here has elected to write the natural log of 1/2 as negative natural log of 2. It is true that that equals negative natural log of 2. If I were doing this problem, I would not make that conversion. I would stick with this, type the natural log of 1/2 into my calculator, and then hit divided by 1590, and I'd get my k value. And then I would hit store in the bottom left corner of my keyboard, and I'd store it in alpha k, which on my keyboard is, it's above the left parenthesis. However, it's more convenient, I guess, to write our k value like this. Either way you write it is totally fine. You're going to have the correct k value, and notice that your t value is still in there. So I can't help myself. If I were doing this, I would write that my k value is equal to the natural log of 1/2, or 0.5 would even be easier to write. Let's do that. Natural log of 0.5, and then you have to take that and divide it by the 1590. So that's my k value, and then I would write that m of t is equal to my initial value, or amount of my radioactive substance, which was 100 milligrams, times e to the my k value, natural log 0.5 over 1590 times t. I don't know why that's any less tidy than writing it this way. So again, whichever way you want to write it is fine. It's fine with me. I'll never see. Let's see. So one of the perks to writing it the way that the author has chosen to write it is that if you take this negative sign and you associate it with the t over 1590, then you've got 100 times e to the natural log of 2, and then you can think of that as being to the power of negative t over 1590. Remember that if you have a thing to a power, you can multiply the powers. So that's why these are equivalent. And then e to the natural log of 2 is just equal to 2, says here. So we knew that because e and natural log cancel each other out, which means now the 100 can come down to here, and the e to the natural log of 2 cancel out, or rather become just a 2, and we can write this as 2 to the negative t over 1590. Yeah, I don't know. Great. I say store this number in a variable. With the advent of calculators, I don't think we have to go ballistic with our algebra in order to simplify this statement down to this, but it works. It's clever. So however you want to write your m of t equation. I write my m of t equation like this in the top right. The author writes the m of t equation like this. If you're doing your homework in WebAssign, you should be able to type it in either way. The mass after 1,000 years. Take a t-value of 1,000, plug it in. You're into the calculator anyway. Part C wants us to find the value of t so that m of t equals 30. So we want an answer of 30. We need to figure out the t-value that's the correct input. So we've got our equation here. This is the format that the author is using. The only unknown there is t. The right-hand side of the equation is m. No, it's not. It's m of t. It's 30. So we're starting out with 100 milligrams. We want to end with 30 milligrams. We want to know how long does that take. Divide both sides by 100. Take the natural log of both sides. You have to do all of your algebraic manipulations, and you end up with a left-hand side of your equation. Well, your equation ends up looking like this after you take the natural log. And then you could just multiply both sides by the reciprocal of this, and you'll have your t-value. Approximately 2,762 years. Now you get an A for watching me talk about how the author wrote it, whether I'm happy with the way that he wrote it or not. Doesn't matter. You get an A for watching. I highly recommend that whether you do it now or you do it later, I would try to redo this problem. This is so nice that you've got this whole written out solution process, the calculation of the k value, all of it, every step. Go through and see if you can do all of these different things in order to get down to a final answer of, where did it go? 2,762 years. And then applaud yourself, because that's a lot of hoops to jump through in order to get there. Here's a graphical interpretation of our model, and then m equals 30 has also been graphed, and we found the point of intersection between our curve and a mass of 30. The x-coordinate of that point is the t-value, which should correspond to approximately 2,800. You can do that in your grapher, like this TI-84 that I was using. Type those two equations in there in y equals mode, and then y equals, that's the graph of something else, and then if you hit, well, I also have to graph 30. And then if you hit second calc, which is above the trace button up here toward the top, hit second trace, that'll put you into calc. And then on my calculator, if I scroll down to the number 5 where it says intersect and I hit enter, then I'm in intersect mode. If you want more details on how to use intersect mode on your grapher, you're already in the right place. Stay in YouTube and find an appropriate video. It should be pretty short. Newton's law of cooling, I believe, is our last topic or subtopic in this section, or our last example of the application of this idea of the derivative of a function equaling a constant multiple of the function itself. Newton's law of cooling, you should read, it relates the temperature of an object to the temperature of the surroundings, the ambient temperature, and the amount of time that it would take for the difference between those two temperatures to change, essentially. And this one's a little bit tricky because this y value that we've been seeing in this differential equation is now a little different than we're used to. That y value is going to represent the difference between the current temperature of our object and the ambient temperature. If we frame it up that way, then we can take this equation and we can write it as this equation so that it fits the correct format so that we can use modeling using an exponential equation. So let's look at it with some real numbers. We know that we prefer these conversations using real numbers. A bottle of soda pop, which is how people refer to soda in the Midwest, and as I understand it, the Pacific Northwest, probably other places. But a bottle of soda pop at room temperature, which is 72 degrees Fahrenheit. So you're starting with a bottle of soda at 72 degrees Fahrenheit, and you're sticking it into a refrigerator where the temperature is 44 degrees Fahrenheit, which I think is a little warm for a refrigerator. But anyway, we're also being told that after half of an hour, the soda has cooled from 72 degrees down to 61 degrees. And we're being asked to find the temperature of the soda after yet another half hour. And then part B, how long does it take for it to cool to 50 degrees Fahrenheit? So our solutions. So T is going to represent the temperature of the soda after T minutes. T sub S is going to represent the surrounding temperature, the ambient temperature, which in the refrigerator is 44 degrees Fahrenheit. So Newton's law of cooling states that dT dt, which is a little tricky, is equal to K times the difference between the temperature of the object and the ambient temperature in the refrigerator. So we're going to let y equal T minus 44 so that we can frame up our equation in this alternate format. And we can attack the process of modeling using the exponential. We should also note that our starting temperature, or I should say that y sub 0 is equal to our starting temperature minus the ambient temperature. So y sub 0 ends up equaling 28. And we're going to have to circle back around to this idea that y is equal to T minus 44. So don't lose sight of that. So our starting y value is 28. That's an initial temperature difference. It's an initial value, but it's an initial temperature difference of 28. So we take that 28 down here and we drop it in place of our C value because it's our initial value, y sub 0 equals y sub t equals 28 times e to the kt. So we still don't know our k value. Does it seem like there's a pattern emerging here? We're given enough information in order to figure out our initial value, which is our capital C value, which is m sub 0 or t sub 0, or ultimately it's y sub 0 or y of 0, which is 28 in this case. And then I'd be willing to bet you that our next task is to find the value of k. All right, so we're given that 30 minutes later, the temperature of our object is 61 degrees, which means that 30 minutes later, the difference between the temperature of our object and the ambient temperature inside of the refrigerator is only a difference of 17 degrees now. And so we see that 17 appearing on the right-hand side of the equation because that is y of t. It's the difference between the two temperatures, the object and the ambient, 30 minutes in, is equal to the starting difference between the soda and the ambient temperature of the refrigerator, 28 degrees difference, times e to the kt. And here again, we're seeing the k and the t have been switched. It's being written as tk, so don't let that throw you off. That's a time value of 30 minutes that's been plugged in there. And sure enough, the only thing that we don't know in that equation is the k value. Divide both sides by 28, and you get e to the 30k equals 17 over 28. Take the natural log of both sides, and then divide by 30, and you will have your k value. Here's an exact value. This is an approximation of what's going to appear on the screen of your calculator, which you can store in the variable called k. And then we take that k value and we put it back into our initial equation. Y sub t equals c times e to the kt, or you could think of this as y sub t equals y sub 0 times e to the kt. And what's happening here, this is a little bit confusing, so I came in and I wrote these notes ahead of time. Remember that the y value was representing the difference between the temperature of our soda, or whatever the object is, in this case it's a bottle of soda, and the ambient temperature, or the surrounding temperature, inside the refrigerator, which I said was too warm. If we take that little equation, y equals t minus 44, and we add 44 to both sides, you get y plus 44 equals t. If you rewrite the equation from right to left, you get t equals 44 plus y. Why did I do that? Because this equation says t equals 44 plus y. So there was a bit of substitution that happened there. On the third line, we see that we're really on our way to answering that last question, which is, what is the temperature after another 30 minutes? Well, we knew that 30 minutes in, we had already brought our temperature down to 61 degrees. Now we're seeing that after another 30 minutes, so 60 minutes into the cooling process, the bottle of soda has been in the fridge for 60 minutes now. It has reached a temperature of 54.3 degrees. Now, are you nervous at all about the 54.3? Is the 54.3 the difference between the soda and the ambient temperature in the refrigerator? It's not. This is the difference between the ambient temperature in the refrigerator and the bottle of soda. And then you increase that by the temperature inside the refrigerator, which is the 44 degrees, and you end up with what is actually the temperature of the bottle of soda. All right, so we see it's written for, so after another half hour, the pop has cooled to about 54 degrees Fahrenheit. So again, you want to be keeping track of the rhythm of these styles of problems. You're given the initial scenario, you're given some initial data, and then the first thing that we did was determine how are we going to frame up the equation. In this case, we had to do this little unusual maneuver where we said that y was going to equal the difference between the temperatures. Okay, that was unusual from what we saw in the previous or the preceding examples. So once we had our equation framed up like that, then we put it into the format that was going to allow us to write our model as an exponential function. So we saw that the derivative dy dt was equal to k times y. And then we plugged in the initial value in order to find our k value, or sorry, our capital C value in the equation where the right-hand side is equal to c times e to the kt. The left-hand side changes depending on what we're modeling. And then once we had our c value, so building the equation just as a wireframe, as a skeleton, that's step one. And then step two was finding that initial value, which takes the place of capital C in front of e to the kt. And then we use the next batch of given information in order to calculate our k value. Now we've got c and k, which means the only thing that we don't have is the input value, which is a t value, and the output value, which is, in this case, the temperature of a bottle of soda, or the number of years that it took to degrade, the remaining mass of our radioactive substance. Okay, so we don't have the input and the output value, but we've got capital C and we've got our k value. The only thing we don't have is input and output, which means the very next thing that's going to happen is the problem, the homework assignment, the test question is either going to give us an input value or an output value. And we'll have to solve for whichever one they didn't give us. And in order to do that in these types of problems, you have to have a really good working knowledge of how to manipulate the equation using natural logs. You have to know that property where you can take the exponent and bring it out front like it's a coefficient. You have to know that the natural log of e to a power allows the natural log and the e to cancel out, and that power just falls down onto the ground so that you can really work with it and manipulate it. So you have to pay attention to the big picture, or I recommend that you pay attention to the big picture, the rhythm of the problem, and make sure you know some of the little maneuvers that are going to allow you to navigate the details and the algebra of the actual solution process. When will the bottle of soda reach a temperature of 50 degrees? We take 50, see they're giving us an output value, and they're asking us to solve for the t value, which is the input value. Subtract 44 from both sides, divide both sides by 28, take the natural log of both sides, divide by negative blah, blah, blah. You run the calculator, you get approximately 92.6 minutes. That's about an hour and 33 minutes. This is just sort of a little side note that says that if we waited for a super long time, if we take the limit as t goes off toward infinity, if we wait for a really long time, graphically we can see what happens to the temperature of the bottle of soda. It heads in the direction of 44 degrees, but it's never actually going to reach that ambient temperature inside the refrigerator of 44 degrees. There is one other little subtopic, compound continuous or continuously compound interest. This won't take long because this is a topic that you're more familiar with. Remember that if an amount a sub zero, it's a starting amount, is invested at a particular interest rate r, for example 0.6, which would be an interest rate of 6%, then after t years, its worth would be equal to this, because we're taking that starting dollar investment a sub zero and we multiply it by 1 plus the interest rate over and over and over again. That's compounding our interest annually. That's what this equation is. Capital A equals this. That's the formula for compound interest, or your final value after compounding your interest annually. Now, if you compound your interest more frequently than annually, you need to use this equation. Capital A, your final amount, equals a sub zero, your starting amount, times 1 plus, you take your interest rate, you divide it by the number of compoundings per year. So if you're compounding quarterly, then your end value has to be a 4. If you're compounding monthly, your end value is a 12. If you're compounding daily, your end value is 365, approximately. And so on. And this exponent up here is n times t, where t is measured in years. So n is the number of compoundings per year times the number of years. So if you compound annually $1,000 at 6% interest for 3 years annually, you get a final amount of $1,191.02. If you compound twice a year, semi-annually, half the interest, see that says 0.3 instead of 0.6, but twice as many compoundings, not twice as many years, it's just twice as many compoundings because you're getting 2 compoundings per year. Then you end up with more money at the end. And if it's quarterly, you end up with another $1.50 or so. And if you compound monthly, you end up with even more. And if you compound every day, these are only very small differences. But we're looking at a modest interest rate with a relatively small starting amount of $1,000. Now, if we send the number of compoundings per year off to infinity, in other words, if we apply the limit as n goes to infinity to mostly to this, a sub 0 is a constant, we could really bring that out front, then what happens is you get this weird mutation that happens because, here we go, what happens in here, or after some more algebraic manipulation in here, what happens when you apply that limit is that you get the number e on the inside of those square brackets. And we're right back where we started. Final amount equals starting amount times e to the RT. So again, your rate is being expressed as an R instead of a K. If we take the derivative of this equation, derivative of the left-hand side, derivative of the right-hand side, using the chain rule, we have to multiply by the derivative of that exponent in there, so that's why we get this multiple of r in front here. Allows us to say that with continuous compounding of interest, the rate of interest, or the rate of increase of an investment is proportional to its size. A prime equals k times a. We previously saw this as dy dt equaled k times y. So it takes on that same format. Interesting. So example 4, returning to our example where we were investing $1,000 for 3 years at 6% interest, we can see that with continuous compounding of our interest, plugging in the $1,000 as our a sub 0, our initial value, and we were given our k value of 0.06, our time value of 3 years, we're in the calculator, and we get a final answer of 1197.22. How close to this is the amount that we calculated for daily compounding? Pretty darn close. But the process of using this formula for continuous compounding as opposed to having to plug in an n value of 365, much easier to just go all the way to continuous compounding instead of 365 days a year. That is the end of these notes. And my other notes that I wrote tell me that I wanted to look at a couple of homework problems with you. And I think I'm just going to create the separate video. So I will see you in part 2. Can I do this correctly this time? There it is. Click right there. Ready, set, go.